Welcome to today's paper reading. Today's paper is titled, Beyond the Contact, Discovering Comprehensive Affordance for 3D Objects from Pre-trained 2D Diffusion Models. This paper was published on AR14 by Hyeonwoo Kim and colleagues from Seoul National University. ComA is a novel affordance representation that goes beyond traditional human-object contact models. It models the distribution of relative orientation and proximity of vertices in interacting human meshes, capturing not only contact patterns but also spatial relationships. The construction of ComA involves a novel pipeline that synthesizes diverse and realistic 3D human-object interaction (HOI) samples using a pre-trained 2D and painting diffusion model. This pipeline includes an adaptive mask and painting framework to ensure the generation of accurate affordances. Experimental results show that ComA outperforms existing methods that rely on human annotations, particularly in its ability to reconstruct 3D human-object interactions and incorporate both contact and non-contact properties. Figure 1 illustrates the process of generating numerous 3D human-object interaction (HOI) samples for a given 3D object using text prompts. This process leads to the learning of a novel affordance representation called Comprehensive Affordance (ComA). ComA is designed to model both contact and non-contact patterns in HOIs, capturing the full spectrum of human-object interactions beyond just physical contact. In this introduction, we will discuss the concept of affordance, which refers to the potential actions an object offers to a user. Affordances play a crucial role in human-object interaction, influencing how people perceive and use objects. Understanding these interactions is essential for effective design and usability. Additionally, we will introduce the diffusion model, a tool used to analyze and predict the spread of information or behaviors. This model is particularly useful in studying how affordances and interactions evolve over time. ComA is a novel representation designed to model the distribution of both contact and non-contact patterns during human-object interactions, HOIs. It encompasses spatial and orientational relations, capturing typical 3D relations between human body parts and objects. To build ComA, we utilize a pipeline that synthesizes a large-scale dataset of synthetic 3D HOI samples using a pre-trained 2D diffusion model. This approach is scalable to any 3D object and does not require manual annotations. Additionally, we introduce adaptive mask and painting, a method that preserves the original context of an image while inserting humans, and enables 3D lifting from 2D HOI cues. Figure 2 illustrates typical human-object interaction patterns. On the left, people use a laptop by viewing the screen from a relatively distant distance. On the right, people use a telescope by peering into it from a close distance. The pre-trained diffusion model demonstrates knowledge of these orientational and spatial relations between humans and objects during interaction. Figure 3 provides an overview of our method for learning comprehensive affordance, ComA, for 3D objects. The process is divided into two main parts: generating 3D human-object interaction, HOI, samples and learning ComA from these generated samples. In the first part, we use an in-painting diffusion model combined with our adaptive mask and painting technique to create 2D HOI images. These images are then uplifted to 3D, resulting in a large-scale synthetic dataset of 3D HOI samples. The second part involves aggregating these 3D HOI samples to create distributions for relative proximity and orientation between human and object surface points. These distributions can be derived into various affordance forms, which are used to learn ComA. This method allows us to model both explicit contact and non-contact patterns during HOIs, providing a more comprehensive understanding of human-object interactions in 3D. The concept of visual affordance was introduced by Gibson, focusing on functionalities provided by the environment to agents. This concept has been extended to vision and robotics, where the goal is to teach agents to interact with scenes. However, learning affordances beyond simple contact points has been challenging due to limited data. In the area of data synthesis, generative models like GNs and diffusion models have been used to augment data for various vision tasks. The main challenge here is maintaining control over the generated data. Lastly, diffusion models have shown promise in generating realistic images, but there are challenges in specifically generating human-object interaction images. Our approach differs by focusing on maintaining the context of the original image during in-painting. The method for learning comprehensive affordance, ComA, for 3D objects involves generating 3D human-object interaction, HOI, samples from 2D HOI images. These images are initially created and then lifted into 3D, resulting in large-scale synthetic samples. The learning of ComA is achieved through Poisson disk sampling to select 3D surface points and mesh vertices. A density function Pn is used to represent the joint probability of relative position and orientation. 3 types of affordance functions are defined: contact-based, orientational, and spatial. The contact-based function, contact, Pn, evaluates proximity and normal alignment. The orientational function, orientation, N, measures the consistency of human body orientations. The spatial function, spatial, P, counts the occurrence of human surface points relative to the object. Figure 4 illustrates the critical role of adaptive mask and painting in preserving the original object's geometry during the insertion of human figures. Without this adaptive approach, the original object is often damaged or altered, leading to the generation of false affordances that do not accurately represent the object's true interaction possibilities. This damage results from the in-painting process, where the object's details within the mask region are not preserved, causing significant distortions. The adaptive mask and painting method progressively specifies the in-painting region over diffusion time steps, ensuring that the object's geometry and details are maintained, thereby preventing the creation of misleading affordances. This preservation is crucial for generating accurate 3D human-object interaction samples, as any discrepancies between the 2D in-painted image and the original 3D object can lead to incorrect representations of how humans interact with the object. Thus, the figure underscores the necessity of adaptive mask and painting in maintaining the integrity of the original object during the in-painting process. The experiments conducted in this study utilize a variety of 3D object datasets for both qualitative and quantitative evaluations. For qualitative evaluation, 3D object meshes are obtained from Behave, Intercap, ShapeNet, and Sapien datasets. Specifically, 20 objects are from Behave, 10 from Intercap, 2 from ShapeNet, and 8 from Sapien. For quantitative evaluation, the Behave dataset is used as a ground truth to verify the quality of generated 3D human-object interaction (HOI) samples. Additionally, 60 free 3D object meshes are collected from the internet source, Sketchfab, to learn comprehensive affordance (ComA). Figure 5 presents qualitative results demonstrating how comprehensive affordance (ComA) models distributions of contact, orientation, and spatial relations during human-object interactions. The figure shows contact scores as heat maps for various objects, indicating conventional usage patterns. It also visualizes the orientational tendency of human body parts relative to the object, highlighting fixed orientations due to attachments or restrictions. Additionally, the spatial relation distribution shows the relative positions of the human body during interactions, aligning with general human usage for objects with multiple utilities and geometries. Figure 6 illustrates the concept of pointwise affordance knowledge as provided by ComA. This model differs from previous studies by focusing on the distribution of relative orientation and proximity for all human-object vertex pairs. This allows ComA to offer detailed insights into how specific body parts interact with objects. For instance, in the case of a motorcycle, ComA can determine that the saddle contacts the human's hips and the handle contacts the hands. Similarly, for a chair, it identifies that the seat contacts the hips and the backrest contacts the back. Additionally, ComA can infer the probable direction of the head when interacting with objects like a monitor, maximizing cosine similarity when gazing towards the screen, indicating a plausible head direction during such interactions. Figure 7 illustrates the application of ComA in reconstructing human-object interactions (HOI) through optimization. This process can be scaled to other objects within the same category by transferring knowledge between them. Specifically, it shows how ComA enables the generation of plausible 3D HOI samples from T-posed humans, even for objects with multiple modes of affordances. The mode-seeking algorithm is applied to 3D HOI samples with their vertex normals to learn ComA separately for different affordance modes, such as swing in the example provided. Additionally, the figure demonstrates the transfer of ComA learned from a specific object to other objects with different geometries through object canonicalization and finding vertex correspondences, thereby scaling the human optimization task to other objects in the same category without additional learning. Table 1 presents the quantitative results on behave sequences, focusing on the similarity of contact distribution as evaluated by SIM and MAE metrics. The table compares our method with IAGNet and DECO across different datasets, highlighting the performance in terms of SIM human, ME human, and MA object. Key metrics include a SIM human of 52.82% and 70.55%, MA human of 0.126 and 0.246, and MA object of 0.0288 and 0.0329. These results underscore the effectiveness of our approach in modeling the distribution of relative orientation and proximity for human-object interactions. Table 2 presents a comparative analysis of the performance of background preservation between vanilla in painting and adaptive mask in painting. The key metrics evaluated include RMSE background, MIU, and MIU occlusion aware. The results indicate that adaptive mask in painting significantly outperforms vanilla in painting in all three metrics. Specifically, adaptive mask in painting achieves a RMSE background of 15.33 compared to 42.23 for vanilla in painting, an MIU of 0.706 versus 0.535, and an MIU occlusion aware of 0.815 against 0.631. These findings underscore the superior background preservation capabilities of adaptive mask in painting, ensuring that the generated images more accurately reflect the original object's characteristics. In this paper, the authors emphasize the significance of learning non-contact patterns in human-object interactions, HOIs, and introduce a novel affordance representation called ComA. ComA is designed to model both contact and non-contact patterns. To learn ComA, a pre-trained 2D diffusion model is utilized, which already has prior knowledge of affordance. The authors design a rendering and painting uplifting pipeline to generate 3D HOI samples and learn ComA from these samples. The results indicate that ComA effectively models the common usage of objects in terms of contact, orientation, and spatial relations. Additionally, the authors propose adaptive mask in painting, which allows for the insertion of humans without damaging the original image, and evaluate its effectiveness both qualitatively and quantitatively. The authors anticipate that ComA will serve as prior knowledge for various downstream tasks, demonstrating its potential through a human optimization framework and the possibility of transfer to various objects within the same category. Thank you for watching.